All right, so back to our factoring process. We've talked about three techniques, right? The greatest common factor, the sum and product method, although there were kind of two versions of that. The sort of standard one when the leading coefficient is 1, and the expanded one when it's not. And then we talked about the difference of squares. So we have these three techniques. In the next set of examples, they're going to be all kind of mixed together, and sometimes you'll need more than one technique for a problem. So quickly, just by way of review, when you're trying to factor a quadratic polynomial, the very first thing that you always want to do is to see if you have a GCF. Okay? That's always step one. Right? It may not, in which case you can just go on, but if there is a GCF, of course, you want to factor that out first. What you do next is really going to depend on how many terms you have. If your quadratic polynomial only has 2 terms, the only way you can factor it is if it's a difference of perfect squares. Right? If so, we've talked a bit, this is just a slightly different version of what I had on the previous page, but we've talked a little bit about how you can factor it as the sum of the values times the difference of the values. If it's not both a difference and perfect squares, at this stage we are done. If there's 3, right, so we're counting 2, if there's 3 terms, a trinomial, then how we proceed is going to be sum and product, although again a little bit different based on the leading coefficients. If we have a 1x squared, we can jump right in and we know it's x times x and use our sum product method to get the p and the q. If it's not 1, if it's something else, we have to use that expanded or extended sum and product method. But either way, trinomials, we're going to want to use sum and product. All right, so let's see. On the next page, we have 6 examples. They're kind of all mixed up, so we got to really think about which technique we're using. As I look at the first one, I'm going to notice it is a trinomial, but I always look for a GCF first, and 4 would definitely go in there. Now, with a leading coefficient that's negative, I definitely prefer to factor out the negative. So negative 4 is going to be the GCF that I'd like to use. When I do that, I'm going to get x squared minus 4x and then plus 3. I can now concentrate just on what's inside the parentheses. It's a trinomial, so I already know it's going to be sum and product. And in fact, now that the negative 4 is factored out, I only have a 1x squared, which is really nice. I can use that shorter method, right? So I'm going to keep the negative 4, the GCF, out in front, and I'm going to say I know in advance my 2 binomials have to start as x times x. Then I'm looking for a sum of negative 4 and a product of positive 3. Not a whole lot of ways to get 3, right? 1 times 3. And if I make both of those negative, the product is still positive 3, but they add up to a negative 4. So that's it. My factored form is negative 4 times x minus 1 times x minus 3. All right, let's try B. Just a binomial this time. And looking at that, I do see a GCF. We always want to think about that greatest common factor first. 5 goes into both, and also t to the first. So when I divide that out, I'm just going to get 1t, and 80 or negative 80 divided by 5 would be negative 16. The t is already factored out. All right, can I go any further with that? Actually, I can't. Notice that this t is not squared, so everything now is just t to the firsts. I'm done. You don't have a quadratic anymore. You can't factor any further. All right, compare that to C, which is a very similar problem, right, other than the variable I chose to use. Other than that, the only difference is this had the t at the end. This just has a constant term at the end. But look how different this problem is going to end up. I'm still going to start by factoring out a GCF, which this time is just going to be 5, right? Can't factor out an x because the second term doesn't have one. So my first term is going to end up as an x squared. My second one a minus 16. This time, because I still have a quadratic, I still have an x squared, I need to think about whether I could factor any more. And the answer is actually yes. This binomial is a difference of squares, right? The x is clearly already squared, and I could think of the 16 as 4 squared. And so I'm going to use that difference of squares pattern, x plus the 4 times x minus the 4. And notice you got that negative 16 popping back in there. Now I have no more squares in there. Now it's completely linear in each factor, and so I know I'm done. All right, what about D? Checking for a GCF always first. This time I don't think I have one. Nothing is going to go evenly into all 3 of those. So I'm going to jump right into one of my other factoring techniques. It's a trinomial, so it's going to have to be sum and product. And looks like I can't get away with saying it's just a leading coefficient of 1. I wish I could, because then it would be shorter, but this one's going to have to be the expanded sum and product. So sum is going to be negative 7. For the product, I have to multiply the 4 times the negative 36. And this looks like a calculator is going to be helpful again. Negative 144. All right, let's see what we can come up with. I'm going to just start dividing by 144, or 144 by different things. I know 1's not going to work. 2 and 72, also no good. 3 and 48, not getting that sum of 7 yet. 4 and 36, I don't think 5's going to work at all. Nope, doesn't come out evenly. 6 and 24, we're still not getting a sum of negative 7. 7 doesn't work. 8 and 18, we're getting a little closer, but still no sum of negative 7. There it is, 9 and 16. If I use my negative correctly, I should make that work. And in fact, the 16 would have to be the negative, so that when you add, you get negative 7. Positive times negative gives me the negative product as well. All right, so my expanded sum and product method, I keep my 4w squared, but I break apart that middle term as a positive 9w and then a negative 16w, and then I bring down that minus 36. All right, I've created the 4 terms now, so I can treat them in pairs. And in my first pair, I don't think I can take anything but a w out, so that's what I'll do. Makes that 4w plus 9. Here, notice there's a minus sign between my groups, so I will want to factor out a negative. And I guess 4 would go into both of those, so I'm going to factor out a negative 4. Makes that a positive 4w. And negative divided by negative again makes that a positive 9. It's working because my 2 binomials in the parentheses here do match. So I'm going to factor out that binomial of 4w plus 9, which leaves me the w minus 4. And just a reminder on any of these, if you think something might have gone wrong, you can always remultiply and check to make sure you get back what you started with, right? That factored form should be equivalent to the expanded form we started with. All right, couple more. So in E, our given expanded form is a squared plus 16. No GCF. And the fact that this binomial has a plus and not a minus here means it's not a difference of squares, and it must be prime. And then finally F. Again, we always look for that GCF first, and this time I think we're going to be able to factor out a 2. So let's do that first. Makes that 3c squared plus 5c plus 4. All right. Trinomial in the parentheses, so I'm thinking sum and product. And with the 3 as the leading coefficient, it's going to be the expanded sum and product. So I'm looking for a sum of 5. And my product, 3 times 4, is going to have to be 12. I don't think that's going to work, is it? 1 times 12, 2 times 6, 3 times 4. It's the only way is to get a product of 12, and none of those are going to add up to 5. So actually I can't factor it any further. But notice, unlike this one where I called it prime because I couldn't do anything, technically this one's not prime because I did factor out a GCF. So this would be considered the factored form for that expanded form. Right. All right, so those are my 3 major factoring techniques for this section: GCF, sum and product, shortcut and expanded forms, and then the difference of squares. Now, we started out, I'm just going to remind you of this because it's been a minute, right? We started out by saying that quadratic functions could come in 3 different forms. The expanded or multiplied out form, which we've seen a lot, the factored form, which we've just finished working with a lot, and then this vertex form that we haven't seen very much yet. We've been given a couple of problems in vertex form and been able to get the factored or expanded forms, but not a whole lot. And what we haven't talked about at all is how to take a function that starts in one of these forms and turn it into vertex form. So that's the very last thing in this section. The process for taking an expanded form and turning it into a vertex form is something called completing the square. I'm going to also mention that if you had a factored form and you wanted the vertex form, the way to do it would be to take the factored form, multiply it out to get the expanded form, and then change to vertex form. So if I can go from expanded form to vertex form, I've kind of covered all of it. All right, so this completing the square process allows us to change expanded form to vertex form. For the purposes of this course, I'm going to give you a couple of examples, and I'm going to keep them fairly simple. In fact, I'm only going to do the leading coefficients of 1. This technique is something that you're going to see more and more in later math classes as you go along, and they'll expand on it and make it a bit more complete later on. I want you to at least see the basics right now so you have something to base that on, but we're not going to go into all of the more complicated cases in this particular class. All right, so here we go. I've got my expanded form right here, and I want the vertex form. First thing that I'm going to do is I'm just going to kind of use parentheses to separate the terms that have x's from the constant term, right? I haven't really changed my function, I've just kind of separated it out a little bit differently. Here's what you need to do to complete the square. This 6x, originally it was that middle term, right? You're going to take that coefficient, that 6, and you're going to cut it in half. You're going to divide it by 2. So in this case, I'm going to get 3. I'm then going to square it. So 3 squared would be 9. And I'm going to add that. Okay. So middle term, divide it by 2 and square it. And add that inside your parentheses. Now the problem is I've definitely changed my original function, right? I can't just add something to a function and think it's the same. It's a totally new function now. So in order to fix the fact that I added 9, I'm also going to subtract 9. That way the net effect is I really just added 0, right? A positive 9 and a negative 9. All right. Take what's in the parentheses and factor it. It's a 1x squared. So for this trinomial, I know I can start with x times x. And then I would want a sum of 6 and a product of 9. It's got to be 3 and 3, right? So I have x plus 3 times x plus 3. And then I can combine those. Positive 2 and negative 9 makes that a minus 7. All right, since I have two factors that are the same when I multiply something by itself, another way of writing that is squared. So what I actually have here is x plus 3 squared minus 7. That is that vertex form that we talked about. Something squared plus or minus a constant. Right? We're going to do one more of those, but I just wanted to point out there's a couple things here that I've kind of done to make this relatively simple as this particular process goes. I picked a nice even number here so that when you divided it by 2, you didn't get any fractions. For our purposes, I will do that just to give you the opportunity to practice this technique. But certainly odd numbers could happen in there, in which case you'd end up with a fraction that you had to square. Not a big deal. You'll see it later. The other thing I want to point out is the problem that I just did had a leading coefficient of 1. It was 1x squared. That does lead to significant other issues if that's not a leading coefficient of 1. And again, I'm not going to address that in here. You'll address that more fully in later classes. So let's try one more of these kind of simplified examples of completing the square. G of t is t squared minus 10t plus 15. And I'm going to start by separating off the parts that contain a variable, t squared minus 10t, and then the plus 15. Okay. Same process. I take this middle term and divide it by 2. It's going to give me negative 5. And then I'm going to square that. Negative 5 squared would be positive 25. If I add 25, I also have to subtract 25 so that the net effect is I've just really added 0. All right, I now want to factor the trinomial that's in the parentheses. And again, for our purposes, we'll always have just a 1 as our leading coefficient. So 1t squared has to start as t times t. And then I'd be looking for a sum of negative 10 and a product of 25. And I'm thinking negative 5 and negative 5. We'll do that. And then on the outside of the parentheses, I have a minus 10. So I could rewrite that as t minus 5 squared minus 10. There's that vertex form, something squared plus or minus a constant. All right, as I said, that's as much as we're going to do here. I will just point one little thing out to you. Did you happen to notice that after I divided by 2, That number that I got is actually what ended up in my square. That's actually not an accident. That happens every single time. And that's something that you can actually use to your advantage right now in terms of like shortcutting your factoring process when you're doing this. But also when the problems get more complicated in later classes, it's a good thing to kind of take note of. All right, that brings us to the end of what we're doing here in section 3.1. Again, really quick recap. Our big thing here is our big takeaway, 3 forms of quadratic functions: expanded form, factored form, and vertex form. We'll be back with section 3.2 in the next video.